Welcome. Today we're going to be taking a look at the notes worksheet entitled Inverse Trigonometric Functions Day 2. And so this would be the middle day in a 3-day set, talking about really the three inverse functions: inverse sine, inverse cosine, and inverse tangent. We've laid the foundation for inverse sine and inverse cosine. So what we'll do is start out today's lesson dealing with the graph of inverse tangent of x and going over some examples dealing with that. So let's start it out here. It looks like at the top of your page I do have the investigation. It does say inverse tangent function. And so what we're going to do is repeat some of the stuff we did yesterday with this. If you remember correctly, what we're going to have to do is restrict the graph in order to make it one-to-one. So what I'm going to do is bring my calculator up. And I know it says it on your sheet here, but I'd like to at least explore it a little bit. So if you get an opportunity, just kind of grab your calculator there and make sure you're in radian mode for me. And then just type in y equals tangent of x. And if I hit zoom in number 7 there and I get my tangent function, which we all know pretty well at this point, we obviously see that this does not pass the horizontal line test. And so as is, it will not have an inverse, that is a function. So what we want to do is restrict the domain in order to make this one-to-one, in order to make it pass the horizontal line test. And so, of course, everybody, it's going to be this piece right here. Again, there are multiple intervals to choose from. This is the most standard, and this is the one that's defined. So from negative pi over 2 to pi over 2. But notice, of course, negative pi over 2 is excluded from the domain because we have a vertical asymptote there. And pi over 2 is excluded from the domain because we have a vertical asymptote there. So as you can see on your paper, and let me go ahead and kind of circle this, we're going to restrict the domain interval from negative pi over 2 to pi over 2 for our tangent function in order to make it pass the horizontal line test, which will make it one-to-one, which means its inverse will be a function independently. So let's go give this a try here. I think this will be the third time around drawing a picture just like this. So let's make this one count. Just something like that should do. And in reality, all you need is 4 tick marks here, and each one will just be pi over 2. So I'm going to go pi over 2 there, and then negative pi over 2 over here, and then just try to keep things somewhat balanced. Here's pi over 2 up here, and everybody, here's negative pi over 2 down here. And so the goal, of course, is to restrict the tangent function from in between negative pi over 2 and pi over 2, exclusive though, so not including those. And again, I think we all know what that tangent function looks like, kind of like this, give or take. Probably draw it a little better than I just drew it there, but that's all right. And then what we would do here is, of course, draw the inverse of that function. And I'm going to go ahead and just sort of get us rolling on that piece and put it up here. And then actually, here's what I'll have you guys do on your paper, if you would. Since we had vertical asymptotes for the graph of the function, we actually have horizontal asymptotes for the graph of the inverse. So if you can go ahead and play those out on your paper, that would be great. And I'm just thinking here that I would like to label one thing. So before I forget, everybody, and if you could do the same on yours, can you go ahead and label that graph that I drew in there as y equals tangent of x? And again, that would be the restricted version, of course. And if we drew this nicely here, and, it's not going to be perfect, but it'll be pretty decent. Should look something like this, give or take. That would be the graph of our inverse, everybody. And if I had my little y equals x in there, and you don't have to do this if you don't want to, but if I had my graph of y equals x, should look pretty good here, a nice reflection line. So what we have now is the graph of the function y equals tangent of x restricted, and then everybody, I do have the graph of its inverse. And so that would be y equals the inverse tangent of x. I'm going to go ahead and just pick up the calculator here if my drawing doesn't do it justice, and that may well be the case. Let's go ahead and at least bring the calculator up to go ahead and illustrate this. I'm going to leave this graph up here. Obviously, when we're talking about this piece, this is the only one I'm focused on. But I'm going to go back to the y equals and type in inverse tangent of x. And you guys can either do this with me or just kind of watch on your screen there. But basically, let's get those two taken care of, and maybe that'll do better. So you can kind of see what I was attempting to draw here. Here's your nice little inverse tangent. in correlation with this one right here. Okay. These two have, well, let's see, two vertical asymptotes, and here, guys, two horizontal asymptotes. And hopefully that makes pretty good sense to you. Switching all of the x's and y's on the initial function gives us the inverse function. Okay, well, we might have an opportunity here to connect these two things, so if you get a chance, let's go ahead and do that. And might not be a bad idea to go ahead and see if you can do it yourself, and then come back and see if you've matched up what I have. But let's see what we can do with this. First and foremost, I guess I would talk about the domain of the restricted tangent function. And so this is our restricted interval. And we could start relating it to the inverse sine and inverse cosine as well. If you remember, we restricted sine between negative pi over 2 and pi over 2 inclusive. But we restricted cosine from in between 0 and pi inclusive. So this one is very much like sine, from negative pi over 2 to pi over 2, except no or equals right there. Well, what do we know about the range of a tangent function? All the tangent intervals are covered in that one interval, and as a matter of fact, it goes from negative infinity all the way to positive infinity. It looks like I cut off my blank down here, but that's all right. You probably have it on your sheet. Obviously, everybody, if I want to go ahead and create the domain and range of the inverse tangent, I'm just going to switch. So these become our inputs, which would be the tangent ratios. And we're going to talk a lot about this tomorrow, try to put it all together for you. So the ratios are the inputs of the inverse. And for a tangent, I can have any number as the ratio. And everybody, the angle measure in the restricted interval. That's where we have to be careful. The angle measure in the restricted interval is the output. And remember, this is kind of what I put an asterisk by for sine and cosine, and I'll do the same here for tangent. And so as we all know now, our answers, our outputs for inverse tangent, let me make sure I got the proper variable for you. So have to be in between negative pi over 2 and pi over 2. And that's looking pretty good. Okay, so now we've developed our third and last inverse trigonometric function. And we'll go ahead and play around with this a little bit with the tangent piece, do a couple operations on the back side here. Tomorrow's lesson, everybody, the day 3, is really where we put it back all together. We'll review sine, cosine, and tangent. We'll do it visually, and we'll really do it conceptually. We'll talk about some good pieces together. All right, well, let's go to the next piece then. So let's see what we have, examples 1 and 2. It says find the exact value of the expression. And so what we're going to go ahead and do here is use these as our tangent ratios. And remember how a function works, everybody. One input produces one output. So what I have to do now is find the right angle measure, in radians, of course. But even though there are an infinite number of angles that have a tangent ratio of √3, I need the one in our interval. That's the key. Okay, so let's give it a try over here, everybody. If you get a chance, can you kind of draw that circle like we did yesterday? And let's see, let's kind of just do this piece right here. I like that. And remember, I've always stated this, we're kind of starting at that initial point, and from there we're trying to go ahead and find the closest spot that has the particular ratio. So for tangent, everybody, we're either going to rotate down to get the negatives or up to get the positives, clockwise and counterclockwise, up to pi over 2 or down to negative pi over 2. So I would include that piece right there. And if we do that, if we rotate either clockwise or counterclockwise, we're going to cover every tangent ratio in existence. Now we have our special tangent ratios, of course, everybody, and so I'm going to include those 3 terminal sides right up here. Those are just kind of the special values that we've been looking at all semester long. So something like that would do. And then let's go ahead and see if we can figure it out. You really do have to know your unit circle pretty well to be successful with this. But that diagram, I think, will help as well. So let's give it a try, everybody. A, B, C, and D. Let's see if we can run the board here. So inverse tangent of square root of 3. And so again, sorry for being redundant here, but we're looking for the angle measure in our restricted interval that has a tangent ratio of √3. The reason for restricting this is to make this a function, because there are an infinite number of angles that have this tangent ratio. In order for it to be a function, though, if this is the input, I can only have one output. And so we want to find the proper output there. So let's go for it here. I'm going to start right here, everybody, on my little diagram. And where am I going to get a tangent ratio of root 3? Well, as I move upward, remember, tangent ratios increase. This one is the root 3 over 3. Here's the positive 1, and here's the root 3. So this is where I'm after, right there. And what is that angle measure in radians, of course? Well, that would be pi over 3. And so that's your answer. Inverse tangent of root 3 is pi over 3. If you grab your calculator, and there's no need to do that at this stage, but if you were to grab your calculator and do this, this would produce that. Input producing output. Okay, let's do letter B. Inverse tangent of -1. So go to your diagram, everybody, if you would. Start at 0 and ask yourself, where am I going to get a tangent ratio of -1? Visualize it if you can. Well, first and foremost, tangent ratios are negative down here, of course, so down this way. And let's go ahead and count it out. Here's where I would get negative root 3 over 3. Here's where I would get that -1, and so here it is right here, and I rotated clockwise from here to here. What would be that clockwise measurement? And of course, it would be pi over 4 clockwise, so negative pi over 4 is our answer. This, as the input, produces this as the output with this function right here. Okay, good. Let's go get letter C. Inverse tangent of 0. So start here, everybody, and think to yourself, where am I going to get a tangent ratio of 0? And as a matter of fact, tangent ratio of 0 is right here. I don't have to move a muscle. So in this particular case, what would be my angle measure, of course? Well, it looks like it would be 0. So inverse tangent of 0 is definitely 0. And by the way, just trying to make connections here for you. If you look at the graph of inverse tangent, here it is. Take a look. When the input is 0, of course the output is also 0. Excuse me. So that gives us that point right there. 0, 0 is a point on the inverse tangent function. And again, here's that case. The tangent ratio of 0 is right here. What's the angle measure that produces it? It's 0, of course. And then how about this last one on my set here? Letter D, inverse tangent of negative root 3 over 3. And so just kind of think to yourself, as you start here and you're picturing this diagram, again, a lot of good visualization with this, do I go counterclockwise to get negative tangent ratios here, or clockwise to get my negative tangent ratios? And it looks like I'm going to go ahead and go clockwise. And in this case, it looks like, where am I going to get that negative root 3 over 3? I believe it's right here. And so in this particular case, I'm visualizing this as a negative pi over 6. So if you know your ratios really well from way back when on the unit circle, this should be second nature. It's just a different perspective on it, whether it's inverse sine, inverse cosine, or inverse tangent. You definitely have the background to pull this off. Okay, well, let's take a look. Example 2, we'll just grab the calculator here, just let it do most of the work for us. It says use a calculator to evaluate the expression to 4 decimal places. And I've got just a quick fill in the blank there. Your answers for inverse tangent, of course, will always be in between negative pi over 2, which again is about negative 1.57-ish, and pi over 2, which of course is about 1.57, ... And that's it. When we do all 3 of these, or any one for that matter, when we take the inverse tangent of any number, and by the way, I can take the inverse tangent of any number. The domain, as we said, for inverse tangent is all real numbers. Well, when I take the inverse tangent of any number in existence, I will always get a number in between negative pi over 2 and pi over 2. This is all reals. This is in between negative pi over 2 and pi over 2. And that's what we developed. So let's just get the calculator going there. And I'm just going to go to my main screen, type in a little bit. You guys do it with me as well. And just nice and simple. Inverse tangent. And so you're asking the calculator to come up within the restricted interval what angle in radians, or what real number, has a tangent ratio of 2.8. And that would be it right there. So to about 4 decimal places, I have about 1.2278 radians. This would be the angle measure with this tangent ratio right here. And notice, look at that number. Do you see it's in between this and this? Of course. Okay, let's continue. Inverse tangent and negative 9.65. Again, so you're asking the calculator to come up with the angle measure in our interval that has a tangent ratio. Remember, tangent ratio would be y over x on the coordinate plane. So a tangent ratio of about negative 9.65. And so that would be it right there. To about 4 decimal places, negative 1.4675. Okay, very good. And then the last one, remember, we can have any number as the tangent ratio. And that's why we said before, the domain of the inverse tangent is all real numbers. So here's just a rather large contrived one. Let's go for it. Inverse tangent, 12,345.67. Something like that. And guys, I'm going to press enter there. And notice what we get, as a matter of fact. We get a number fairly close to pi over 2. So let me first and foremost go ahead and write that on the board here. So that would be the answer. That would be the angle measure in radians, or the real number, that has a tangent ratio of this right here. And notice this number, certainly it's close, but it is in between negative pi over 2 and pi over 2. It's probably a little below pi over 2 right there. So that's why there's a dot, dot, dot right here. So this pi over 2 is probably slightly larger than this angle measure, which is pretty close to it, as you can see. As this goes to infinity, this gets closer and closer to pi over 2. Okay, great. So now we've again defined inverse sine, inverse cosine, and inverse tangent. Again, I promise we will take a look at the next page there and really put it all together. There's some good stuff to be had still. Okay, so what we're going to look at on the back side of your notes worksheet is really just reinforcing the intervals that we've developed. They're somewhat contrived algebraic expressions, but I think they're good to really reinforce the idea that sine is in between negative pi over 2 and pi over 2, cosine is in between 0 and pi, and tangent is in between negative pi over 2 and pi over 2. So I think this will help us out a little bit. They're going to get a little tricky. I'll try to walk you through as best as possible. So I have a little investigation to get us thinking at least about what's going to happen here, and then we'll go ahead and attack the problems that you see at the bottom. So it says on the top of your page, applying opposite operations on an input. And so bear with me on this for just a couple minutes, and let me see if I can sort of describe what's going to happen here. So we're going to start with an input. And it says add a number to your input and then subtract the number. Will you always end up with the original input? So think about this for just a second. If you started with a number, pick a number, and then what you're going to do, you treat that as your input, and then you're going to add something to that input and then subtract the same thing after that. So if I start with 5, and then I'm going to say add 4 and then subtract 4, would I end up with my original input always? And the answer, I think, would be yes, certainly. When I add and subtract those opposite operations there, addition and subtraction, I always get back to the original input, of course. Okay, seems rather elementary. Bear with it, though. Okay, what happens if I start with an input and I multiply a number and then divide by that same number? So except 0, as it says on your sheet here. So start with an input and then multiply something to that input and then take that and then divide it back. Will I always end up with the original input? And I think the answer, of course, would be yes. So if I multiply and divide, opposite operations, everybody, I get back to the beginning, of course. Now, guys, let's take a look at number 3. What happens if I square my input and then square root my input? Will I always end up with the original? Now, think about this one for just a second. So I'm going to just go ahead and start with an input. Say I'm going to start with 4. I'm going to square 4, and I get 16. And then I'm going to take the square root of 16 and get 4. Yes. Start, finish. Same. Okay, that sounds great. But what happens if I start with something like this? What happens if I start with negative 4, everybody? Well, I would square it and get 16, and then take the principal root of principal root of 16 and end up getting 4. Here's where I start. Everybody, here's where I finish. Do I end up with the same input? No. And so here, guys, is a situation where even though they're opposite operations, they don't undo one another that in a way that will get me back to the original input. I hope everyone's okay with that piece. Addition and subtraction? Yes. Multiplication and division? Yes. Square and square rooting? Not necessarily. And so that, everybody, is what this next piece is. And these are the opposite operations of one another, sometimes called a composition. And so take a look at it. The nice thing about these notes worksheets is you don't have to write it down. They're right there for you. But what we want to do is kind of look at it and see what it entails. So again, they are in the same vein. They are opposite operations. And basically, they are called compositions of one another, either the function and its inverse or the inverse and the function. Now, as you can see, take a look just at the top one there. When I compose the function of its inverse for a particular value, I get the original value. I start with this, and I end with this. Only, though, in certain situations. Only if our values are in the proper interval. And that's the key, everybody, is to know the proper intervals. So all 6 of these are ones that we're going to develop, so please keep them in mind. I would argue probably, and I'm just speculating here, that really 2, 4, and 6 are probably going to be the harder ones for you. And so those are the ones we'll investigate in good detail. But notice, everybody, when I do the inverse sine of the sine of x, in order for me to start and finish in the same position, the only way that occurs is if our numbers are in the restricted interval for sine. So does everyone see that? There's your restricted interval for sine, everyone, from negative pi over 2 to pi over 2. Look at cosine, everybody, the fourth one down, from 0 to pi. And everybody look at tangent, the last one down, from negative pi over 2 to pi over 2. These intervals should match up with everything we've talked about. If you look at the 1, 3, 5 very quickly, sine ratios in between negative 1 and positive 1, cosine ratios in between negative 1 and positive 1, tangent ratios, of course, can be any number. So it really solidifies some good ideas that we've been developing. Well, as I said, they can get tricky, and there's only one way to kind of go through it, and that's together. So it looks like I have just a quick little blurb here before doing the example 2. And it just says, even though the above operations are opposites, you do not necessarily, so let me underline that piece, sometimes you do, sometimes you don't, just like the square and square root. So you do not necessarily end up with the original input. So what we're going to do is just kind of walk ourselves through, excuse me, we'll go back and forth there. For me, I'll go back and forth board to board and just highlight some ideas, and you guys hopefully will kind of figure it out. So here we go. I'm going to do the inverse sine of the sine of pi over 4. Now, everybody, these two are opposite operations of one another. So theoretically, they would cancel each other out, and I would be left with exactly what I started with, pi over 4. But this only works, they only cancel each other out, and I'm left with this if pi over 4 is in the right angle interval for sine. So, guys, I go on back, of course, and this would be the number 2 up here. Just looking at it right here, is pi over 4 in this interval right here? Is it in between negative pi over 2 and pi over 2? So if you can visualize our diagrams, well, especially from yesterday, is pi over 4 in between these two numbers? Yeah, absolutely. And so as a result, if I were to do the inside operation and then the outside operation, these two would undo one another, and everybody, I would be left with pi over 4. Pi over 4 is in the restricted sine interval. Think about it that way. Okay, that's good. That's your first answer. Letter B, everybody. Now, again, here, opposite operations. Taking the cosine of the inverse cosine of 0.6. Now these two should undo one another, and we would be left with what we start with, only if 0.6 is in the proper interval. So the question, of course, becomes, and this goes really to number 3 here, this matches up nicely, is a 0.6 a proper cosine ratio? Is that a ratio in between -1 and +1? Absolutely. And as a result, because 0.6 is a good cosine ratio, then taking the inverse cosine of 0.6 and then the cosine of that answer brings us back to the beginning. And so that's 0.6. Okay, letter C. Let's take a look at this one. Inverse tangent, tangent, -pi/6. These are opposite operations of one another. They should undo one another, and we would be left with this, with what we start with. But that only works if -pi/6 is in the right interval for tangent. And so think about the interval for tangent, of course. Let me go back to my screen here. This would be the last one. So right here, everyone, this is -pi/6. Is -pi/6 in this interval here, everybody? Can you envision going clockwise? Yeah, certainly. And it is in between -pi/2 and pi/2. And because it is definitely in the proper interval there, those two do undo one another. And I started at -pi/6 and I end at -pi/6. Okay, now we shift gears. A, B, and C, perfect. D and E go together, everybody. So let's take a look at this piece. Sine, inverse sine of 2. Now remember what this means, guys, when I take the inverse sine of 2. I would be looking for the angle that has a sine ratio of 2. Now if you sort of look at this, first and foremost, where it matches up, this would be the first one. Can I ever have a sine ratio of 2? Does that make sense to have a y/r ratio for any angle be equal to something above 1? No, of course. In fact, you see it right here. Sine ratios can only be in between -1 and +1. And so if I can't even do this, well, these two can't cancel each other out and have me be left with a +2 here. I can't even do that operation. If you were to try to do the inverse sine of 2 on the calculator, it would automatically give you an undefined. And so, as a matter of fact, just to quickly show you this, inverse sine 2. And you know this to be the case. That's not possible. That's outside the domain. So not to mention trying to do that second piece, and here I'll do the whole thing here, simply doesn't work. I can't have that operation occur. So because this 2 was outside the interval, we can't even do it. Now that's going to be a little different than the next set, but just keep in mind that piece. All right, everyone, letter E. How about this one? Cosine, inverse cosine of 1.1. Understand what the expression is trying to tell you, and you have a shot at this. This is basically saying, find the angle that has a cosine ratio of 1.1. Well, everyone, I mean, is it even possible to have a cosine ratio above 1? No. And if I go back, of course, here we are, just one more time. This is number 3 here. Here's this number, but this only works, of course, for cosine ratios, and cosine ratios have to be in between -1 and 1. And so as a result, everybody, this one right here simply does not work. That's undefined. Okay, so when our number is outside of that interval, we don't get what we started with. In this case, with D and E, we can't even do it. They're undefined. Now, here come the 3 hard ones, F, G, and H. So here's the idea, everybody. We can do these. We're going to get answers for all 3 of these. But you will notice that each of these 3 numbers, this one, and this one, they're outside the interval as defined at the top of your page. So how are we going to deal with that? So I would encourage us to sort of, until we get very good at this, and I can give you a couple shortcut ideas as we go through the process, just work from the inside out, try to evaluate the inside expression first, then apply the outside expression. And I'll tell you what I mean by that. So first and foremost, let's do one thing here. Inverse cosine, cosine 3 pi over 2. So I go on back, everybody, and this would be, of course, this one right here, number 4. 3 pi over 2 is our input. But does everyone see that 3 pi over 2 is obviously not in the restricted interval for cosine? It's not in between 0 and pi. So 3 pi over 2 is not going to give us 3 pi over 2 right here. But it is going to give us something. And so let's figure out what that something is by, again, just understanding what the expressions are telling us. So guys, this is something you've been doing ever since the beginning. You know what the cosine of 3 pi over 2 is. It's the x to r ratio at an angle measure of 3 pi over 2. Think on the unit circle, and I guess I could get you to sort of picture it as the inverse, I'm sorry, let me catch myself up here. The cosine of 3 pi over 2, I hope everybody would realize, is 0. So the cosine ratio at that angle is 0. By definition, that's something we know. Now everybody, this is something that we developed yesterday. So we now look at this. We apply the secondary part to the expression. And I ask myself very simply, what is the angle that has a cosine ratio of 0? Well, as we have alluded to, there are an infinite number of angles that have a cosine ratio of 0. The problem here is I've defined this as a function. So if this is my input, I can only get one answer as my output. And that answer has to be in a particular interval. For cosine, it has to be somewhere from 0 to pi. And so ask yourself this, of course, what angle in that interval has the cosine ratio of 0? And you know this. It is at the top of the unit circle. It's pi over 2. And so that's your answer. So when I did this, I got the ratio of 0. When I did this, I got the angle with that ratio, but back in our proper interval. So what you're going to ask yourself very simply, and again, it's going to take experience with this, but you're going to, if this is outside the interval, what you're going to try to do is find the angle with that same ratio in our interval. So pi over 2 has the same cosine ratio as 3 pi over 2. Pi over 2 is in the interval. 3 pi over 2 is outside it. Okay, and that's how it's going to work. Let's try another. See what we can do with this. Okay, so really know your intervals for sine, cosine, and tangent. For tangent, everybody, it's in between negative pi over 2 and pi over 2. And so obviously in this particular case, this is outside that interval. This is not in between negative pi over 2 and pi over 2. So we can do this though. I just have to think about it from the perspective of let's do the inside expression first, then apply the outside expression. Now guys, this is old news. We know the tangent at pi. Tangent ratio at pi is 0. And by the way, just coincidence, that's the same as the last one. So tangent ratio at pi is 0. But now everybody, when I say to myself, what is the inverse tangent of 0, I'm trying to find the angle measure within the interval, from negative pi over 2 to pi over 2, that has this tangent ratio. And as we saw, as a matter of fact, let's go for it. Let me see if I have it on the board here. Let's go back one more. Here it is, guys. We did this. Inverse tangent of 0 is, there it is, everyone. Take a look. It's 0. So that was right here. Look, there's our diagram for tangent. We're going to draw all three tomorrow. But basically, as you can see, here's the tangent ratio of 0 in the interval from negative pi over 2 to pi over 2. And so that's it. That's your answer. So notice 0 as an angle measure has the same tangent ratio as pi. This one's in the interval. This one's not in the interval. So that's our answer, the one in the interval. Okay. Last one here, and then you'll get some practice on this. And again, ask some questions. We'll walk you through as best as I can, of course. So I go to this one right here, and I say inverse sine of sine of 2 pi over 3. These should undo one another, and we would be left with 2 pi over 3 only if 2 pi over 3 is a number in the proper interval. And for sine, is 2 pi over 3 in the proper interval? No, because for sine, the proper interval is from negative pi over 2 just to pi over 2, and this is beyond that. So I'm not going to get 2 pi over 3 here, but I am going to get something, so let's get it to work. So I would work from the inside out until you get really good at this. Basically, I would ask myself, what is the sine of 2 pi over 3? And I know this from the unit circle and other developments over the course of this curriculum. I know that it's root 3 over 2. Okay, so now I apply this piece. Well, what is the inverse sine of root 3 over 2? So now I think back to yesterday, and I think about from negative pi over 2 up to pi over 2, there is an angle measure with this sine ratio. And what is that angle measure, of course? I guarantee you it's on yesterday's notes worksheet, and should be able to pull this off as pi over 3. And think about this. These two angles have the same sine ratio. This one is in the interval we want. This one is not in the interval we want. And so that's why this is our answer. One more drawing here just to illustrate. If you've got this, you're good to go. But basically, here's 2 pi over 3 right here. Here's pi over 3 right here. And as you can see, they have the same sine ratio. There they are, same sine ratio. This one is outside our interval. Again, our interval is from negative pi over 2 to pi over 2. So coming here and down here, this is the one for sine. So as you can see, this can't be our answer because it's outside the interval. So I say, oh, wait a minute. Which one has the exact same sine ratio inside the interval? And there it is, guys. There's pi over 3. Okay, the best thing to do is to just try some out, get some practice with it, of course. I'm available, of course, to help you. And then tomorrow's notes worksheet, there's not a whole lot of development there. There's one new type of problem. But basically what we'll do is just rehash, review, really try to derive some meaning with all this stuff. I know it can be a little confusing. So get some practice on it, and please ask questions. Thanks for listening to the lesson, of course. I appreciate it.